back. Today we are going to discuss about quantum teleportation. It is basically a way of transfer a quantum state. That means the information stored in one qubit to another qubit without moving the particle. Okay. It works using three main ideas. First thing is nothing but entanglement. You know what is entanglement, which is a special quantum connection between two qubits. And secondly, it works on classical communication where after measurement, two normal bits of information are sent to one person to another. Okay. So the third one is nothing but quantum gates. As already we know, CNOT and Hadamard gate, which help combining and separating the qubits during the teleportation process. So CNOT and Hadamard will be very key in quantum teleportation. In simple terms, the sender's qubit is destroyed after measurement. So after measurement, sender will be destroyed. Sender will be no longer there. Okay, and the receiver qubit becomes exact copy. So sender receiver will collapse and receiver will have exact copy of sender. Okay, so the quantum state moves but the particle doesn't. The main uses are in secure quantum communication, that is that is what forms the basis of quantum internet. It also used in quantum key distribution, okay, which provides unbreakable encryption, and for distant quantum computers using entanglement will be using quantum teleportation. Now moving on to the quantum teleportation circuit. This is how quantum teleportation circuit looks like. So if you observe here, if we are having a message get psi, that is nothing but alpha get 0 plus beta get 1 will be our message, and we want to send, this is nothing but this complete, we call it as channel. Okay, this is nothing but channel of teleportation. So we are sending our message alpha get 0 plus beta get 1 with the help of Alice. Okay, with the help of her we are sending it to Bob. Okay, we want to send this alpha ket 0 plus beta ket 1 to Bob, applying this operation. This is nothing but we call it as CNOT gate. Okay, this H is nothing but Hadamard gate, that we already know, and these symbols are nothing but we call it as measurements. So quantum teleportation is nothing but without physical connection we need to send the information. So already Alice and Bob are entangled. If they are entangled, A and B are entangled, let us say. So the formula for entanglement is nothing but 1 by root 2 1 ket 0 0 plus ket 1 1 is the formula, right? So now I will explain what is this. X and Z are nothing but poly X gate, poly Z gate. I will explain why I have integrated these gates in the circuit. So this is what about quantum teleportation circuit. So the thing is, we need to send this message to Bob by applying some gate operations. Okay, that is how we need to send. So how these calculations are going to be held and how we need to progress this quantum circuit, I will explain step by step. So moving on to the starting point. So already I said qubit 1 is nothing but the information qubit. Okay. So qubit 2 and qubit 3 are entangled. Then the equation will be same as I wrote earlier, 1 by root 2 ket 0 0 plus 1 by root 2 ket 1 1. So now, so this is ket psi 1 is nothing but message. Okay. That is nothing but first qubit. And this state represents Alice and Bob. Okay, so I have combinedly writing this. This is nothing but we call it as tensor product. Okay, tensor product. So tensor product, how tensor product is done is nothing but ket 0 tensor product with ket 0. You can write combinedly ket 0 0. So if you look at here, we will be having alpha ket 0 plus beta ket 1. This is first qubit, right? Tensor product with 1 by root 2 ket 0 0 plus ket 1 1. This is 2 3 2 3. Okay, so if you multiply this alpha ket 0 with the whole term, you will be ended up getting this. If you like look into here, alpha ket 0 1 by root 2, I have to common. Okay, alpha ket 0 into, that is nothing but tensor product with ket 0 0, alpha ket 0 tensor product with ket 1 1. Same way beta, now beta 1 you multiply or do the tensor product, beta ket 1 1 into ket 0 0 2 3, beta ket 1 into ket 1 1 2 3. So now if you look into the gates, so I'm again moving on to, so till now here we are. Okay, now we need to move a step forward. In the next step we are having, for first qubit and second qubit we are having CNOT. Okay, this is CNOT. Okay, I will erase this for your better understanding. So we have done until this part. Okay, now we are moving on to the next part, that is nothing but CNOT. So this is nothing but control. Okay, if you are not familiar, please refer the video of quantum gates. Okay, and this is nothing but target, as we already aware. Okay, now we combinedly wrote the system, and next step is nothing but we are applying CNOT gate for Q1 and Q2, that is nothing but information qubit and Alice. So what happens if you look into this particular slide? So if control is 0, I am again quick recapping, target will be 0 and target will be same after applying the CNOT. If control is 0, target is 1. If control is 0, target won't change in the both cases. Now please look here, control is 1, target is 0 and target becomes 1 after applying the CNOT. If control is 1 and target is 1, after applying CNOT, target will be flipped. So that is how control target qubit works in teleportation or in quantum gate operations. So now we are applying the CNOT. So we are applying for first qubit, second qubit, again first qubit, second qubit, first qubit, second qubit. This is second qubit. If you look here, so I am taking out some common. Okay, from, sorry, so if you look here, if I take 1 2 common from here, I will be ended up getting ket 0 0, 1 2 again common here, 0 1 1 0 in beta, 1 1. These are nothing but 1 2 1 2 1 2 1 2. The third one remains constant, but I have just took the common of 1 2 1 2 1 2. So now these are nothing but first and second qubit. Now apply CNOT gate for all those qubits. If you apply CNOT in this particular scenario, you will be ended up getting ket 0 0 only, because control is 0, target won't flip. Here also control is 0, target won't flip, but here control is 1, target flips. Here control is 1, target flips. So what you will be getting here, 1 1 you will be getting, and here 1 0 you will be getting, because control is 1, target is flipping. So same thing I have written here. So this nothing will be happening because the control is 0 in all the cases. Here what happening is nothing but here target is 0 and here it became 1 because control is 1. Same way here control is 1, target becomes 0 because target here is 1. So I think this part is clear for everyone. So this is the small calculation, but the thing is you need to do it very carefully. So now moving on to Hadamard gate. Before moving on to the Hadamard gate, I need to go forward again. So now where we have done until this part. Okay, now we need to apply Hadamard gate on qubit 1. Okay, so please look here. So if I apply Hadamard gate on qubit 1 from this particular equation, so h of ket 0 always creates a superposition with positive sign, that is nothing but ket 0 plus ket 1 by root 2. If it is h of ket 1, it creates minus, adds phase to this particular superposition equation, that is nothing but ket 0 minus ket 1 by root 2. So think now I am taking the first qubit out from the both equations. Okay. So here what happened is nothing but, again I need to go to the previous slide. So here the first qubit is ket0, here the first qubit is ket0. I will make you the simple calculation. H of ket0 is nothing but 1 by root 2 ket0 plus ket1. Okay, h of ket1 is nothing but 1 by root 2 ket0 minus ket1. That is what I have written here. Okay, now what I am doing is nothing but, here in this particular scenario I am applying h here because it is only for first qubit, and I am applying h here. So in this particular result you will be getting 1 by root 2 here and 1 by root 2 here also. So if I take 1 by root 2 common, 1 by root 2, already I am having 1 by root 2 outside. So if I take 1 by root 2, 1 by root 2, then I'll be ended up getting 1 by 2. So this is 1 by 2, and here it should be like 1 by root 2 by root 2. I have took it common. Okay, so I'll be ended up getting 1 by 2. So remaining remains same. So that is nothing but ket0 plus ket1, ket0 minus ket1. I think this is clear. So now what I am doing is nothing but, I am multiplying ket0 with this whole term, and ket11 with this whole term, and ket01 with the whole term, ket11 with the whole term. So what I will be getting? So if you look here in this particular calculation, so after applying Hadamard gate, you will be getting these equations, right? So now you try to do the tensor product, ket0 with this whole term. So what I will get, 1 by 2 common, alpha I will take common, ket0 tensor product with this whole term. Okay, so what I will be getting, ket0 0 0 1 2 3. Okay, ket0 again plus ket0 1 1 1 2 3. Same way, now ket1 with this whole term, again this ket1 with this whole term. So what I will be getting, ket1 0 0 1 2 3 plus ket11 with 1 1. So I will be end up getting ket11 1 2 3. One part is done. Now moving on to beta, I will be taking beta common, ket0 0 with this whole term. So what will I have, ket0 1 0 1 2 3. Okay, again ket0 with this whole term, ket0 0 1 1 2 3. Okay, again this minus ket1 with this whole term, minus, I will be getting minus because there is minus, that is nothing but phase, 1 1 0 ket 1 1 0 1 2 3, minus again this term you need to multiply, ket 1 0 1 1 2 3. I think this part is clear. So what I am doing is nothing but, from this particular step you take ket0 0 1 2, ket0 1 1 2, ket1 0 1 2, and ket0 1 1, okay, 1 2, take common from all those terms. So if you take that common, or I have took here, I have took 1 common, okay, ket1 common. If I take ket1 common from all those terms, I will be ended up getting these results. Okay, so if I take ket0 0 common, you will be here, I will take ket0 0 common. Okay, ket0 0 if I take common from that equation, okay, what I will be getting, if I take ket0 0 here and here, ket0 0 is there. If I take ket0 1 by 2 remains same, ket0 0 common, alpha only 0 is left, alpha ket0 3. Again here in this particular scenario I am having ket0 0 plus beta ket1 3. Okay, if I take ket0 1 common, 1 2, that is nothing but, here ket0 1, alpha ket1 is remaining, alpha ket1 3 is remaining, and if I take 0 1 common here, and I am beta ket0 3 is remaining. Okay, now same way, 1 0 if I take common, 1 0 here and 1 0 here. So I will be having 1 0 if I take common. Okay, get 1 0, 1 2. If I take common 1 0 here, what is the remaining term? Alpha get 0, alpha get 0 3, plus minus will be there because here it is reflecting minus. So if I take my 1 here, the remaining term will be beta ket 1 3. So if same way, if I take ket 1 1 common from all those 1 2 equations, so I will be getting, if I take ket 1 1, alpha ket 1 1 remains ket 3, this is 3, sorry, this will be remaining, and minus, if I take 1 1 common here, minus beta ket 0 3 will be the remaining term. So if you look at here, the actual message is at ket 0 0. Here alpha ket 1 and beta ket 0, you need to apply poly X gate, and here you need to apply Z gate, and here you need to apply X and Z gate. That is why in the circuit, if you go quick recap in the circuit, so that is the reason Bob has X and Z gates at the end of the circuit. Okay, in case 1, nothing, no operation is required. In case 2, X gate is required. In case 3, poly Z gate is required. In case 4, poly X and Z gate is required. So 0 0 nothing, okay, no change. 0 1 you need to apply bit flip error, that is nothing but poly X gate. 1 0 you need to apply phase flip error, that is nothing but Z gate. 1 1 you need to apply X and Z gate. So finally after correction, Bob qubit becomes ket psi is equal to alpha ket 0 plus beta ket 1. This is about the correction. This is about the calculation. Thank you. If any doubts, please let me know in the comment section.